Welcome to Illinois EPA Office of Energy Public Water Infrastructure Energy Efficiency Programs Fall Webinar Series. It's great to see so many familiar names in our attendee list today. So we thank you for coming back. And if you're new to our webinar series, welcome. Thanks for being here. This is our first event of the year, and we're really happy to have you here. So please take a moment to say hi in the chat and let us know where you're coming from today. My name's Cassie Carroll, and I work with Cdac's Technical Director, Sean Maurer, and our Associate Director, Todd Rusk, here at Cdac, the Smart Energy Design Assistance Center, to deliver these programs to you all. Just wanted, before we get rolling today, to do a couple of Zoom housekeeping items before we get rolling. So we will use the chat throughout today's session. We'll ask some different prompts or questions of the audience. Please feel free to use that to communicate with us or to share ideas, thoughts, and comments. If you have questions as our panelists are talking today, please share them through the Q&A box. We will have a Q&A session at the end of our session, so please get your questions ready and we'll answer them in the order that they've been received. This event is also being recorded, so the recording and the slides from today's session will be shared via email either later today or early tomorrow. We'll send that out to you via email. And CEUs. CEUs are coming from the Illinois EPA, but once we get them, we will send CEU and PDH certificates to every attendee. So you don't have to reach out and let us know that you're interested. We will send them directly to you and to your inbox. So thanks as always with your patience in getting those course numbers. All right, I think that's all the Zoom housekeeping today. But let's dig into today's session. Our event focuses on continuous commissioning and really maximizing your treatment plant's energy savings through this concept. Every operator we know monitors their facility daily. However, some things you just can't see from your daily monitoring, and they might go unnoticed during regular checks and data reviews. So really the goal of this session is to highlight key equipment and process checks to identify issues before they become plant emergencies. And I love everybody saying hi in the chat. Good to see you all here today. And again, this is the first event of 5 for this fall for water and wastewater treatment professionals. I do have a slide that I'll highlight here in just a moment that will share all of our different opportunities that we have coming up. So who is Cdac? We are an applied research program here at the University of Illinois. And really our goal is to help entities save energy and money while becoming more sustainable. So we're really working to reduce the energy footprint of Illinois. Now we also have another program partner in the Illinois EPA Office of Energy Public Water Infrastructure Program, and it's the Illinois Sustainable Technology Center. And I'm going to allow Bill Oxel from ISTC to say a few words. Bill?
Well, thank you, Cassie. I was relieved to see that I had an unmute option because I was trying to figure that out all the way up until then. But hello, everyone. My name is Bill Oxel. I'm the program manager on the ISTC side and very happy to be working with Cdac, wonderful group who has helped us a great deal in re-enlivening our program here. And I believe also on the discussion or on the meeting with us here is Andy Krein, who's also one of my colleagues, and we basically are excited about being part of the program and assisting all of you in making your facilities as efficient and resilient as possible, and looking forward to getting to know everybody out there and working with you.
Awesome.
Thank you, Cassie.
Yeah, no problem, Bill. Thanks for chatting today and telling us a little bit about ISTC, the Illinois Sustainable Technology Center. And both of us work with the Illinois EPA Office of Energy for the PWI, or Public Water Infrastructure Energy Efficiency Program. And I'm going to turn it over to my colleague, Sean, to talk a little bit more about this program. Sean?
Well, thank you, Cassie. So a little bit about how this program works. We have partnered ISTC and Cdac with the Illinois EPA Energy Office to offer no-cost assessments for public water facilities, both wastewater treatment and potable water treatment. What we do is we'll work with you to come out to your site, review your facility, figure out some opportunities for energy savings, and then we'll come back to our office, we'll generate a report, and help you figure out and plan how to make those upgrades to your facility and be as efficient as possible. So we provide a comprehensive report that lists the costs of upgrades, estimated payback periods. We'll also review applicable incentives and funding opportunities, grant opportunities. We'll try to connect you with all those materials so that you're as prepared as possible to move forward with any efficiency projects that you may be looking into. So if you're interested in the program, this is actually an old link. It's www.smartenergy.illinois.edu/water. Cdac was our old website address there, but we'll drop that in the chat for everyone here in a minute. So if you're interested, you can go to that site and you'll find an application form. If we could go on to our next slide here. Why might you want to complete an energy assessment? If you're an older existing system or you haven't had a previous assessment, we're going to help you find some missed opportunities. We're going to help you plan for capital improvements. We've gone to a lot of plants that are looking at doing upgrades. They're working with engineering firms and they're trying to plan out how they're going to make their process changes for the future, expansion projects, things like that. We can help coordinate with engineering firms and the existing plant to make that new update as efficient as possible. We can also uncover missed opportunities for existing facilities that aren't planning existing upgrades. We're going to go through and look at, do you have VFDs on your pumps and aeration blowers? Can you upgrade any controls, things like that? Also, a lot of times when we go to existing facilities, the operators there already have existing ideas. They just need a little bit of support for moving forward with funding through their municipality. And we can provide that kind of support with our assessment reports. It gives you a document that details the benefits of doing different upgrade projects, how much money that's going to save on the utility side. And also we try to address any other non-energy benefits like reduced labor hours and things like that in those reports. So you can make the best case you can to your budgetary offices to try to push those projects forward. If you're a brand new plant or you've recently upgraded, we always seem to find that there's some area to improve. Something got left on the table, got budgeted out for cost purposes for the project. And so we can help identify those for future planning and projects. So there's always something that we can find to help plants out. So how do you apply for an assessment? Go to our website. Again, it's www.smartenergy.illinois.edu/water. And there's an application form there. You must be a publicly owned plant. So some of the private firms that are out there like American Water and things like that, we can't necessarily work directly through with the EPA energy program. But you must be publicly owned. You got to allow us to come out to the site and take pictures and review your facility. Be willing to share facility information with us. That way we can help develop the most accurate report possible. And then we do share that final assessment report with the EPA Energy Office. It's not being shared with any compliance offices or anything like that. It's just going to the Energy Office so they can track the effectiveness of this offering. Step 2, we do some data collection. So we come out to your site. We're going to, before we come out to your site, collect your discharge monitoring reports or monthly operating reports if you're a water plant, process flow diagrams, 2 years of utility bills and histories so that we can develop an initial benchmark for how your facility is performing. And we'll compare that against facilities that we've assessed in the past, give you a good idea of how you compare to other facilities in the state of Illinois. And then we'll schedule the site visit and come out and do some assessments with you. So this is our first in a series of fall webinars or workshops. Today we're going to be talking about continuous commissioning. Joining us today is David Schaefer from the Village of Hayworth. He'll be talking about some on-site measurements and calculations that you can do. And then we'll transition to Todd Rusk, who helped with some SCADA data analysis for Kishwaukee. And so we'll talk about both field measurements that you can do to check that your plant is operating as efficiently as possible. And then we'll also look at the data side for those with more complex SCADA systems. And then future presentations, we're going to be digging into energy efficiency topics. But I would like to now turn it over to David Schaefer to go ahead and talk about his experiences.
Thanks, Sean. Should be seeing my presentation here.
Yes, looks good.
Okay, fantastic. So, like Sean and Cassie said, they asked me to speak a little bit about some things that we've done at the Village of Hayworth. And I'll be honest with you, some of it we kind of came about by accident. We weren't specifically setting out to do these items, but this is kind of where we ended up. So as we look at commissioning and figure out why my slideshow doesn't want to change here. What is it? It's really, it's more than just starting it up. It's more than just plugging it in, turning it on and walking away. When you're installing new equipment or starting a new process, you can't just plug it in, walk away. And to some extent, it's more than verifying your overload settings. Your electrician's probably going to check the amp draw. Yeah, the motor's where it should be, or it's close enough. But did you check the flow rates on the pumps? Did the impellers get trimmed correctly at the factory? Did they actually ship you what they said they were going to ship you? Were all your sensors and meters calibrated and checked for proper operation? Were valves in the correct position? And then does it function as it's designed, or as it was intended? People make mistakes during design. Engineers make assumptions. Those assumptions may or may not be correct, or something may have changed if the project got shelved for a couple of years, and some of the assumptions are no longer valid. The plant may operate as designed, but that's not what you intended because things are different. And then, are your operational set points where they should be? From my experience, especially, in the past, water and wastewater facilities really didn't get a lot of commissioning. It wasn't, it was like a no need. It's not important. Or, it's the end of the job. Nobody has any money left. So it's coming out of the contractor's profit. It's coming out of the engineer's profit. And the owner doesn't want to pay anymore because they settled on a price and they've paid that much money. And so it usually gets left to, either the integrator or the electrical contractor to make it work. Just make it work and get out of there. Or the owner or operator is in a push to get the new facility online. Hey, we've been stringing this old place along. I really need this pump station. I really need this, aeration basin, whatever it is. And so, let's hurry up and just get it done. And, we'll figure it out later. Well, it works well enough and later never comes. So what is continuous commissioning? Well, continuous commissioning is, an ongoing process to resolve operating problems, improve comfort, or optimize energy use. For buildings and a lot of structures, it involves, gathering a lot of data and then data mining, looking for trends, looking for changes, trying to predict where things are going to be. Ideally, the data that you're getting, though, is in a form you can readily use, but it also involves observing and addressing issues. So there's a component of that that's O&M related too. If you see a problem, are you addressing it or are you going to let it go? And I throw this picture in here. This is at my sewer plant. Sean came out back in the spring, early spring, to do an energy assessment for us. We're looking to see where else we might be able to squeeze a few more dollars out as energy rates were coming up. And we had a pump there with a bad seal. So our run times were extended. And I knew about it. but I didn't want to do anything about it because I was gonna have to I was gonna have to pull the pump to get the information on it because I didn't have good documentation. And Sean reminded me, is like, hey, you're just sitting there wasting energy while you're, without fixing that, and you're probably talking less than $1,000 for the parts. So pull the pump, get the information, and solve that issue. Well, we'll get into a little bit later. We ran into some other items. We ended up replacing the pumps, and these are the new pumps. But it goes back to part of that continuous commissioning is, if there's a problem, address it or make a plan to address it. So at a wastewater facility, what are the data points that most of us have readily available? That's going to be your motor run times, your flow rates, motor amp draw that may be readily available, might be something you have to measure manually. And then bearing temperature, if you have blowers with exposed bearings, items that aren't submerged. So motor run times is probably something that most everybody has. Most of your motors have hour meters on them. One, they're cheap. Two, it's a cheap way to kind of keep track of things. And three, for a lot of regulatory pieces, it's required to have some information. So the question then is, what are you going to do with the data? The lower left-hand corner of the slide there is one of the data sheets from our lift stations. So someone goes out every day, they write down the hour meters on the pump, that goes on a nice little sheet. At the end of the month, they collect all the sheets, and that goes in a file. And that file probably doesn't get opened until the next month when the next sheet goes in there. On a regular basis, are you comparing run times from, pump one ran half an hour, pump two ran 2 hours? Why? Where was the issue there that needed to be addressed? And then the next question is there a better way to do things that give you data that's more actionable? So on the right-hand side is a copy of part of an email that I get every morning. It takes me about 10 seconds to read it. And what I get is my run times in minutes, an estimate of how many gallons based on the pump run time and a pump rate. I also get how many starts each pump had, and then an average run time for each start. Not a whole lot more data, but it's a lot more actionable. I can do a lot more with it. And to that end, we had a pump fail at one of our lift stations. That was the seal failure went off, so we were going to pull the pump before it got waterlogged and get it repaired. We dropped the spare pump in. Well, the next full day of runtime, I get my report, and you can see pump two was the new pump that was dropped in. My runtime was 13% less than the other pump that was already in there. Well, they're the same model, exact same specification, same horsepower, same impeller, same manufacturer. So then the question is, why is my runtime, different on pump one? And maybe I need to pull that pump and investigate where, do I have rags wrapped around the impeller? Do I have a blockage somewhere else? And so just having a little bit more information can help you to start making decisions to improve your efficiency across the board. The next piece that is a good one to look at is your flow rates. If you have flow meters on your pumps, then verifying the flow rate's pretty easy. You read the meter, write the value down. Every 4 to 6 months, you go back and look at it and say, hey, pump two's slowing down, where our flow rate's not doing so good as it was a year ago. I wonder what happened. Let's pull that pump. Let's take a look at it. But if you're like a lot of smaller systems, and you have small lift stations, you don't have a flow meter. The question is why? You know, I think from my experience, it was always you don't need that. What's the operator going to do with this information, having a flow meter on there? That's just one more thing you'll have to maintain. So now you're left with, I don't have a flow meter. I know my run times, but I don't know what my flow rate is. So how do you overcome that? You know, the obvious answer is, well, cut in your discharge pipe and add a flow meter. That's great if you can afford it and you have the time. But what if you want to get some answers right now? And the next piece of that is to do a fill and discharge or a fill and draw study to determine what the pumpage rates are. So for a fill and discharge or fill and draw study, it's a little bit of math, a little bit of measuring, and spending some quality time, at your lift station of choice. So the first thing you need to do is have the open area of the wet well or the pit that you're pumping out of. So if it's a circular wet well, your pi times the radius squared. So measure your diameter, cut it in half, square it. If you're a rectangular pit, then you're just length times width. And I like to start with the pit, mostly drawn down or pumped down. And I'm going to measure the current water level, and I'm going to start a stopwatch. And usually what I do is I measure from the top, a defined point at the top of the wet well down to the surface of the water. I'll record, hey, that was 12 feet, start my watch, go kick back for a little bit. And then I'm going to come back before I get to a pump on point, and I'm going to measure the water level and stop my watch. And so I started at 12 feet. Now the water level's up to 8 feet. So I had 4 foot of depth change, and say that took, 10 minutes or 15 minutes. Now I have a volume because I have a depth and an area, and I have time. So I can figure out how many gallons came into this pit at one point in time. And if you want to work in gallons, you need to multiply by 748 to convert from cubic feet to gallons. That gives you an incoming flow rate. You're going to basically do the same thing again, but pumping down. And if you have a second person to help you, it's a lot easier to have someone put your pump in the hand and pump down versus trying to guess right when the float's going to trip and do your time and depth measurements. So you're going to pump down, and you're going to measure again your 2 depth values and your time, and you can calculate the volume of liquid that was pumped out. And your pumping rate on this one, though, is going to be the volume that you pumped out divided by the time it took to pump it out. And you're going to add to that your incoming flow rate, because while you were pumping out, you still had flow coming in. This type of a study works best if conditions are relatively constant. So you don't want to do it, at 7, 8 in the morning when everybody's waking up and that morning rush of wastewater is coming into your facility. You want to do it at 2 in the afternoon when the flows are relatively constant over the 10 or 15 minutes it might take you to do this. You're going to want to run each pump separately, and then you might want to run a multiple pump scenario as well. And if you do a little bit of searching on the internet, there are some pre-made spreadsheets for pump drawdown tests or wastewater pump tests. So you don't have to do all the math yourself. Another good data point to collect from your motors is your amp draw. It's probably something you do quarterly if you're doing it manually. And you want to compare the amp draw on each leg of your 3-phase motor. Is the amp draw, are you balanced? How does that compare to past results? How does that compare to your operating point in your startup documents or in the documentation from the manufacturer? In this case here, you can see I'm pulling between 31 and 33 amps. That motor was only supposed to be pulling at the current loading somewhere around, I think it was 22 amps. So obviously we've got an issue that needs to be addressed. If you have, motors or equipment with exposed bearings or end bearings, checking the bearing temperature with a non-contact thermometer near the end of the operating cycle can give you an indication of where you're at, with potential for bearing failure. And the only thing I'd say is make sure you're getting the thermometer that's going to cover the temperature ranges you're looking for. If you're stealing the one from the medicine cabinet for junior, it's probably not going to register a temperature high enough to do you any good. Get something that's going to cover, up into a couple hundred degrees. That way you can also use it for checking asphalt temperature when you're paving roads and doing other things as well. So what do you do with the data that you collect? You're collecting those data points. You want to use them to maintain your plant efficiency and improve where you can. You can also use that to your advantage when you're applying for energy efficiency grants. Like I said, if the motor is supposed to be pulling 20 amps, but when it's tested, you pull 30 amps, well, you can increase the amount of funding you're going to get, because like on the a lot of the energy savings applications are based on their kilowatt hours saved. So for the village of Hayworth, when we replaced the pumps in our dosing tank, we started off our application. Here's where the pump was supposed to be operating, and we weren't going to get a whole lot. In fact, it was likely the application wouldn't have even been funded. We were right at the break point of what they would fund. And the reviewer from Ameren, asked me some questions because he didn't believe I was right with some amp draw, and I was conservative. And we went back out and did a fill and draw study where we recorded the amp readings at various points in the pump cycle, and that's where those readings came from. And we ended up increasing the amount of our rebate by I think it was about $1,500 or more, simply because we were pulling more amps than you would have normally expected from the manufacturer data, and because of how poorly the pumps were operating, the savings are going to be significantly more, which means we should have traded them out quite a while ago. Beyond that, if you're operating with old pumps, looking at where you're at on the pump curve, what's that pump efficiency going to be? You might be, operating in the 40 to 50% efficiency range. It might be time to replace those pumps and push yourself up into the 70, 75% range, if that's a possibility. There's a lot of opportunity if you'll spend a little bit of time keeping track of where your facility is operating at. And Cassie, that's all I've got.
Awesome. Thank you so much, David. That's amazing information. And I'm curious out there, who else on our call does fill and discharge studies? If you want to share a little bit of your experience, that would be fun to hear. But thank you, David. Awesome explanation of what you do at your site to, or at your plant, to really check those different levels and how you use data. I think that's
well,
really.
And I should be clear, Cassie, we don't have this figured out by any means. I mean, there's a lot more things we'd like to do, and it's like, yeah, we need to record these data points. Sometimes they get recorded on a notebook, and then that piece of paper disappears and it doesn't make it back with the rest of them. So, if you're listening and thinking that, hey, we've got everything figured out, by no means. We've got a long way to go, but it's just, do the little things that you can do to keep keep moving forward, even if it's just a small step at a time.
Awesome. Really good point, David. Thank you. All right, I am going to transition now to the Associate Director at Cdac, Todd Rusk, who is going to speak to the Kishwaukee Water Reclamation District and a little bit more about analyzing SCADA data to identify opportunities for efficiency. Todd?
Hi, thank you. Let's see, can you hear me?
Yes, I can hear you.
Okay, and are you able to see my slides right now?
Not yet.
Not yet, okay.
Perfect. Now I can.
All right, great. Got it. Okay, well, before I start, I just wanted to say, David, I really loved your presentation. You're like a data fiend after my own heart. And I have tried so many times to talk about data, and people didn't want to hear it. And so that was great. Really appreciated some of your comments at the start about, you found stuff by accident, because you just go in and you start digging in, and you never know what you're going to find until you start digging in. Some of that is what you will expect, but there's always more. So I like that. Really appreciated the point about doing something with your data. I've seen this just in so many places, not just wastewater and water, but there's so much data out there on SCADA systems and other kinds of systems, and it's just doing something with the data that you're collecting is really important, because otherwise we're leaving value on the table, and we're leaving operational intelligence on the table. It's like we're spending this money and going to this effort and not getting out. So I wanted to reinforce that, and love just going out and making your own data when you need it, doing calculations and manual measurements. And then and some of this I'm saying because I think it's a transition to what I want to talk about, but questioning your set points and your calibration and design basis and operating status to make sure that everything is doing what it's supposed to, and what you intend. These are all great practices to make sure that you're getting the value out of everything that all the resources and money and effort you put into collecting data and maintaining it in these systems. So I'll move over to this is a case study about an evaluation that we did at Kishwaukee Water Reclamation District. Let's see. Okay, there we go. Okay, so we did an energy assessment with Kishwaukee Water Reclamation District back in 2021, so last year. And following up on that assessment, we did a little bit more detailed investigation into some of the SCADA data. So just a little intro on the plant. It's in DeKalb. It's 8 MGD design plant, and then you can see the average flows and dry weather flows. It's an activated sludge plant, and it's a really nice place. It's been upgraded since 2017, and it's got all this great stuff in it. And then I just put a little bit of information on the turbo blowers, because this presentation is about optimizing the aeration systems. And then I guess I just want to also, special thanks to Mike Holland. He was not available to participate in this discussion, otherwise we would have had him on. But anyway, he was great to work with, and he was willing to let us talk about this case study for you all. So just to give you a little bit more, context about what this about this plant and how it's set up. There's a process flow diagram, so you can you can take a look at the details there. Some of the things that I would like to point out are you can see in several places here at the headworks. There's a headworks meter. This is an electrical submeter. The electrical building meter, that's another submeter measuring the electricity use of the aeration equipment. And of course, this is where the blowers come in. That's the biggest piece of that particular submeter. And then there's another submeter for the sludge handling building. And there are some other ones, but along the lines of helpful data points, especially if you're interested in optimizing your energy use and your electricity use, is incorporating electric submeters into your SCADA. We did a lot with that in this particular evaluation. And so if you're interested in tracking that kind of stuff and finding what you can do with ongoing continuous commissioning, electric submeters could be really helpful addition to your systems. So we got into this because with this facility, and we do this at lots of places when we have the data, what we found is the daily electric use wasn't really varying that much with the daily influent flow. And so it was a little bit of a head scratcher, and we've seen it at other places too, but it just raises this question. Well, you expect if you're treating more flow, you're going to have more energy to treat that flow. And it's just really not apparent here. And so we're wondering, well, what's going on there? And, shouldn't there be something? And so, we part of this, we looked at the, with the energy benchmarking, this is this new plant, they have great stuff, great operations personnel. And the energy benchmark, what we have up here, just under 2,400 kilowatt hours per million gallons of flow per year. It's not bad, but we expected with this new facility and all this great equipment that it would be better than that. And so, this was something that we went in with the plant operator, and we were both interested in this. So we dug into it. So after talking things through a little bit, Kishwaukee really, they wanted to focus on a couple areas. They wanted to focus on the electrical building. This is where the blowers, this is the electric meter where the blowers are. And they were also interested in the sludge handling. And the sludge handling, that's a story for another day. I just wanted to focus on the aeration. But as you can see, what we have here is in this table is a breakout of annual electric operating costs for these different areas of the building. And you probably know this in your own facility. Your aeration is a big chunk of your electric use, and that was the case here. They were also interested in, they wanted to dig more into their aeration systems because they had already suspected, they had already known that there was some over aeration going on, and their engineering consultant had been whispering in their ear about, improvements and upgrades that they should be doing or that they could be doing. And so they were already inclined and kind of thinking in this direction. So it was natural to go this way. And so I'll get into the hows and whys and all that kind of stuff. But what we eventually got around to was that, yes, after we looked into the data, it was over aerated and quite a bit. And they have the potential to save $84,000 per year by optimizing their aeration system. And the solution, which as we were talking it through, Mike Holland had it on his desk because of discussion with his engineering consultant, was to replace the core of one of their blowers. And what that would do is, it would derate it and allow it to operate at a lower flow and give them a higher turn down ratio, so that when conditions allowed, they could operate at a lower airflow around their blowers. And the cost to install it was less than $100,000. So it's a really good return on investment for that kind of upgrade. Okay, so that's the answer. That's that's where we landed. And so now for the rest of the discussion, I want to go into some of the data analysis and what do we look at and why, and you know, how do we get there? So you know, I mentioned the plant electric use overall was not changing very much with flow, at least as much as what we expected. So this top graph on here, this is that one. So, you know, what we have is, you know, each data point, I'm looking at this green graph on top where it's electric use versus plant influent flow. We have a bunch of dots. And so they're spread out horizontally according to what the daily influent flow is. And then their vertical position indicates how much electric use occurred on that day in the whole plant. So that's what that top graph is. That was the one I showed you earlier. And so now we're wondering, okay, well, you know, what's the explanation for that? So we dug into some of those submeters that they had on their SCADA system. So we look at the Headworks building, and you know, luckily we see the Headworks building. This is the one at the lower left. As flow increases, the Headworks building electricity, you know, that electricity use increases, which is kind of a relief, because I'm feeling like if, you know, if the Headworks, which is pumping all the influent through the process, if that's not going to be apparent, then, you know, I don't know what to do, and we all just go home. So it was nice to have something like that to grab onto. So anyways, that's not our answer. Sludge handling building, you know, that one really, it also didn't explain what we were seeing. This graph in the middle shows the electric use of the sludge handling area versus plant influent flow. And, you know, it's a little bit, but the thing that we noticed was we scratched that one a little bit more because they were interested in the sludge handling building. And this graph on the lower right is what the sludge handling area is using for electricity versus the sludge feed. So this is, you know, how much of the sludge solids are coming out of the process and going into that building. And so what we see there is a discernible increase. You know, we might like to see a little bit more variation, but you know, it makes sense. You've got more sludge flow coming into the sludge handling area, and the electricity use increases. But still, you know, this you know, we're seeing something, but it's still, you know, we still don't quite have the answer. You know, why is overall this plant not responding the way that we expect it to? And so we looked at the electrical building, which is where the blowers are, and the aerobic digester equipment. And so this is the one that kind of blew my mind for a bit until we had a chance to look into and think about it a little bit more. What we see here is that with this relationship, it looks like as we have more and more flow, we have less and less electricity use by the aeration equipment. And that was a surprise. It seems a little bit strange. So, you know, we just kept digging. And then I guess since we're talking about aeration and optimization, you know, of course, you all know that, you know, everything you do in your process, especially aeration, has a lot to do with your compliance, and nobody wants to risk that. Nobody wants to go there. So let's just make sure, you know, we look at the data, make sure, is there room to make some adjustments and do some optimization? And, you know, we looked at it, verified, yes, there's plenty of room. They're doing fine. You know, they're all, you know, they're in compliance, and there's plenty of room between their limits and where they're actually at. So, you know, so we got to keep going on this, because we still don't have our answer. So if flow isn't really the determinant, then maybe nutrient loading is the thing that matters. So ammonia, does ammonia have anything to do with it? So if we look at this graph on the bottom, you know, as I have more ammonia, it doesn't appear to impact electricity use. And then this graph on top, this box and whisker plot, what this is you know, each little, you know, box and whisker set, those little boxes with the little upper and the high ends and the low ends. What those represent, each one of those boxes represents a different flow range. So at the very left end, it represents, you know, a range of flows from 2.6 to 3.2 million gallons per day, and so on. And so what you see here is which each of these boxes represents, as you go to the right on this graph, what it means is that you have more and higher flow per day. So what this graph shows is on the vertical axis, it's the typical range of your influent ammonia. And so what this is saying is that the flow, you know, the amount of flow coming in on a daily basis, it doesn't really influence the ammonia. They're separate from each other. It doesn't influence it. So anyways, that's what those graphs mean. Ammonia, it does not depend on what the flow is. And anyways, it doesn't impact our electricity use. So that's not what we're looking for. So same thing with BOD. I can go through this one faster. Again, with this box and whisker plot, you know, BOD doesn't really seem to, you know, the amount of flow coming in on a daily basis doesn't really affect how much BOD is coming in. You know, it's different factors contributing to the BOD. And then when we look down in the bottom, it looks like, you know, BOD is influencing aeration energy a little bit, but it's not as much as we might expect. So we're still, you know, still kind of looking. And we landed on, we were fortunate that their SCADA system has, they have a dissolved oxygen sensor on the influent water. So what we found here is that for some reason, as we have more and more flow into the plant, there's also more and more oxygen coming in. And this graph on the bottom is showing that it even shows up in, like, if we look at, you know, over the calendar, you know, what's the orange line and dots, that's our, you know, the influent flow, and then what's the dissolved oxygen level on the influent flow. So they track pretty close, you know, and here it looks like if it's cold outside, my DO is kind of high. And if my influent flow is high, my DO is kind of high. So what's up with that? Maybe it has something to do with I&I. But then, you know, when we go back to looking at energy, this shows it pretty clearly. As we have more and more oxygen coming in through the influent water in the plant, our blowers are doing less and less in energy consumption. And it makes sense. You know, if for some reason, if the outside environment is pumping more oxygen into the water that's coming in, then the blowers and the aeration system has less work to do. So that makes sense. So we let's see, and just a time check here, I'm just a couple of slides left here, so I'll be done and we can wrap up with questions. So, you know, but it really, this point on the bottom, like, okay, well, you know, it's all interesting, but so what? You know, what do we do with this? How do we use this to, you know, get to some optimization? And the answer comes in when we look into some of their aeration tanks and the plant effluent and what the dissolved oxygen level is doing in those. And so what we see from looking at the data is that in these aeration tanks, you know, where they're actively introducing oxygen, now I'm talking about the graph on the right here, when the influent dissolved oxygen level is low, then we're steadily, meeting our process targets for dissolved oxygen. But then when we get to the cases where the dissolved oxygen is elevated in our influent, then what we're seeing is that the process levels of DO is just rising. It's not holding steady at that process target, and the reason is because their blowers don't have the turn down ratio. They can't go low enough so that instead of maintaining that process target, they over aerate when the dissolved oxygen is high coming into the plant. And so we see a similar thing at the effluent. The process overall is over aerating when there's lots of oxygen in the influent. So we've got room to dial back on the aeration and still meet our process targets and still meet our effluent requirements. And in this case, they were over aerating by like 190% average over the year. And so that's a 65% savings potential on their aeration system. That was what we found. And so the conclusions from all of this, kind of a restatement, they've got potential to save 65% on their aeration energy if they can turn down their blowers and make those blower upgrades. The other thing is that there's environmental factors are introducing oxygen into the water that's coming into the plant. And it's a really wide range. If we look back, they have influent levels from 0 milligrams per liter of DO up to 8. That's a really big range. And further, that range, those variations in dissolved oxygen in the influent water is affecting the plant operation and how much the blowers actually need to operate and aerate the process flows. And then the last thing is that there's a role for engineering design here. If their design had taken into account the impact of oxygen coming in from outside of the plant, then they could have had a chance to design a system. Maybe one of the blowers could have been smaller, had a bigger turn down ratio. But when we don't account for those things, the main thing is we're wasting money because we're aerating in excess. So that was what we found, and be happy to talk more with anyone who's interested. Thank you.
Thank you so much, Todd. It's just really, I remember following that investigation in our office and how many different iterations we went through just to really uncover that end result. And thank you for explaining that story and how we got those results and that savings opportunity. I'm now going to turn it over to Sean to kick off our Q&A portion and discussion portion of the webinar.
Okay. Let's see here. Questions. We've had a couple of questions come in about different control systems. One is there a savings difference between smart drives versus VFDs? The main difference between those is a VFD is kind of a dumb controller. You wire it to other things and it responds to those incoming signals, where the smart drive has some logic programmed into it, has safe minimums and response controls kind of built into that drive already. So there can be some efficiency increase from using a smart drive versus a VFD. But if you've got good programming with a standard VFD tied to a SCADA system with the right sensors, you can get equivalent savings. So it's just a packaged version of a VFD control. For David, you talked a little bit about those sand dosing pumps.
Yeah.
Maybe you could go a little bit more detail about how you determined those needed to be resized and
Sure.
did that
So,
work?
so the tank that those pump out of, we'd actually had a valve installed on that line, so we could valve that off. And while we were while I was procrastinating pulling the pump to get the nameplate information to pull the information so we could order the seal kits, the pump that was leaking had ended up, the winding was grounded out, so we were going to have to pull it anyway. So we're trying to figure out where we were on operation point, just to, okay, are we ordering a new pump of the same style? Are we doing something different? So with our existing pump, we did just a drawdown study. Since we were able to valve that tank off, we didn't have to worry about incoming flow, so I didn't have to wait for it to fill up and add in my incoming flow. And that's when we figured out that, you know, this the pumps that we had in there were actually operating closer to 1,600 gallon a minute. And going back through the pollution control board requirements, the EPA requirements under Title 35, the size of those pumps should be based on the twice the flow rate of the incoming pipe to that portion of the facility. So we should have been sized at around 1,400 gallon a minute. And, you know, instead we were actually pumping higher than that. And when you plot that pumping rate against the pump curve for the existing pumps, we were way out of operating range. And that was kind of the one that started, you know, scratching the heads and like, you know, why are we even running these pumps? And then we started pulling the amp draw on them, and it's like, you know, we should be pulling 20 amps based on the pump curve, and now we're pulling 30 some amps. And is kind of a throw your hands up in the air and say, we're just going to scrap everything. You know, they're 42 years old. Why are we even bothering to spend any more time on this? Let's resize for what's appropriate for the facility, and go forward with something that's more efficient. And I believe the pumps we ended up putting in were supposed to be running at about 74% efficiency from where we were at on the pump curve, if I remember. The other thing I wanted to comment on, you know, when we're going back and talking about commissioning, is a lot of facilities, you know, they get designed with this, here's where we want to be in 20 years. And so you end up with equipment that for today, it's just not the right size. And a lot of times, to Todd, what you said, you can't turn it down enough. You know, you don't need, you know, maybe it's, you know, something that big right now, and you spend a lot of money buying something that you may not need for 10 years or 20 years. And I understand you're trying to predict the future, but the future might come when that equipment's already done. So there needs to be a balance between what you're designing for, and, you know, whether you need 2 of something, or maybe you get 3 of something smaller. And that gives you some more opportunities for energy efficiency as well. But you have to balance that with installation cost as well. So having an honest discussion and being honest with yourself about what your growth looks like or what your demand looks like is important.
We did have another question come in about blower system. This particular operator has a blower system that kicks out at 90 amps. Would they be able to reduce that kick out set point to 80 amps? One of the things you might want to consider there is that setting might be there for surge protection for those blowers. So you'll want to work with your blower manufacturer and your aeration designer to make sure that that's not an issue. But there could be potential there, especially as we were just saying, a lot of systems are designed oversized. You may need to look at a smaller blower potentially, rather than trying to modify that existing system. Todd, you talked a little bit about submetering at buildings, and one of the questions that brought up in some of our pre-analysis is demand management at facilities, and looking at can you operate equipment on different schedules to take advantage of like time of day utility scheduling. Do you know at that particular facility, were they using those submeters to try to do some demand side management?
I don't know if they were doing demand management for, keeping their demand charges down. I know that they were, keenly interested in, they knew that they were, I think the big thing for having those sub-meters was that they're interested in being an energy efficient plant, in bringing down their impacts and emissions. And they knew that doing that sub-metering was an important step in that process. And whether there was a demand management, that might be there, but I don't know that.
That has brought us up to our time, and I don't see that any additional questions have come in. But please, if you do have any questions, or this has sparked an interest in some in-depth analysis at your facilities, Cdac is happy to help you out. Please feel free to reach out to us at our website, schedule an assessment. We'll be happy to work with you. If you have any questions for us, you can also reach us through that website link. We'll have a technical assistance line as well to answer some quick questions.
Awesome. Thank you so much, Sean, for running our Q&A. Todd and David, thank you so much for presenting today and taking time to be here with all of us. I hope everybody on the webinar enjoyed today's session. Again, I will send out the recording and slides, as well as CEU and PDH certificates when available. Our next event is implementing automation and time management at wastewater treatment plants. So we will have one session for lagoons on October 11th and another for activated sludge systems on October 25th. So again, visit our website, sign up for an assessment, or just sign up for one of our upcoming events. Thank you so much again for being here today and spending a little bit of your morning with us. We look forward to seeing you soon, and thank you again to our presenters. Take care, everybody, and have a wonderful day. Bye.
Thank you. Bye.
Thank you.